Okay. So, yeah, just a bit of housekeeping. I do my notes digitally, so you can always get a copy of my notes on the right. This will be, available every workshop, and I just recommend that you bookmark it. I think it will be pretty useful. I'll populate my workshop notes every week in there, and just make sure that you've filled out the attendance QR code every week. I'll shut the Google Forms from receiving new entries like sometime after the workshop's closed, but as long as you do it at some point during the workshop, it's all good. And yeah, Taiwan wants the attendance for this course recorded, and you need to attend 80% of the workshops. Okay. Cool. I guess what else is there to talk about? Yeah, my name's Henry. I'm a PhD student, and yeah, I'm a structural engineer. I'm doing my PhD in the realm of reinforced concrete. So this is a topic that I really like. Personally, this is one of my favorite courses at uni, and I hope it ends up also being one of your favorite courses at uni. So I guess it's just a bit of context. Why do I like this course? I'd say there's two reasons why I love this course. Why I love concrete. Yeah, there's two main reasons, right? The first one is the course loves me back, or it loved me back when I did it, right? So what do I mean by that? So you might have done courses before where you liked the content, but you weren't getting the marks back that reflected how much you studied it. So maybe steel structures could be an example of that. But I promise if you put in the work for this course, you'll be able to do well in it, right? It's a very fair, it's a very honest course. I can go over it in a bit, how the assessments will work. But just keep in mind, the way the course works is, yeah, it's 40% of the course is, 40% of the allocated course marks is pre-exam stuff, and then 60% is the finals. And the finals isn't particularly easy, but if you study for it, you'll do well. All right, the second reason I love this course is this is kind of the point in my degree when I did this course where civil engineering made sense, right? So civil degree made sense. And so what do I mean by that? You kind of taught throughout your degree that, I guess you're just expected to know that civil engineers use concrete, right? And you probably heard the fact before that concrete's the most used material in the world, other than water, or the most consumed material. And you're kind of just expected earlier in your degree to accept this as a fact, right? So in 2101, the construction course, it's oh, of course we use concrete because, we're civil engineers, right? In, for example, geotech, the second half of geotech, it's oh, of course we use concrete as a footing for this building because, we're civil engineers. But in this course, what you realize is that there's a reason why concrete is so widely used. So in the first half of the course, we're going to be talking about the material properties of it and why it's so useful for us as engineers, and shaping, I guess, the landscapes of the cities and building these large skyscraper buildings, etc. And then hopefully in the second half, which would be more related to solid mechanics and how to work out, how to design buildings and stuff like that, you'll see that the mathematics behind the course and the physics is quite fun to do. It's quite beautiful, and hopefully it ties together everything that you've learned so far in your degree. Even if you don't want to be a structural engineer in the end, I understand not all of you will want to be structural engineers, but if you get a good understanding of concrete, it'll help you out pretty much no matter what you want to do as an engineer. If you want to be a geotech engineer, you'll understand how the foundations work. If you want to be a water engineer that uses works with dams or with say there's a concrete pipe or something that you're dealing with, you'll have a good background in how concrete structures work. So I love this course, and I hope that comes across as I'm teaching it. All right, so without further ado, we're going to go into the course content. The first few weeks will be largely material science, and I'm not going to lie to you, I'm not the best at things like chemistry, but I'll try my best to explain it the way that I learned it, and hopefully that's at a dumb enough level that everyone will be able to understand the chemistry, I guess, behind it. So we're going to talk about concrete and cement first, and then after that we'll be talking about hydration of cement. And then there's going to be 9 questions in this workshop, and because it's 9 questions, and I'm also going to talk about each of the concepts a little bit first, there's going to be a lot to talk about, so I'll try to pace it well, hopefully. Cool. Yep. All right. So I'm going to just move on. A little bit about the course and how it's laid out. So these are the weeks of content. It's hard to kind of show you the whole thing at once because otherwise it'll be too zoomed out. But in terms of where concrete sits in your degree, of course, in your first year you did engine mechanics, you did material science, and the construction course. This will play into your understanding of how this whole course works. And then in the second year you've done mechanics of solids, and some of you have probably done 2303. It's okay if you haven't. You don't need to know exactly the methods that you learned in 2303 to understand this course, but it definitely helps if you've done it. And then the third year is your design courses, right? So steels and now concrete. So I understand some of you guys haven't done steels and now you're doing concrete, and vice versa. But or maybe you've done steels last term. Either way, you should be able to follow what's going on in this course. So yeah, I'm just going to briefly mention this. So in the first 2-ish weeks, that's material properties and material science. Arguably in the third week as well, but third week we're starting to lean into structural properties, and it's getting more and more close to structural design. And then in the fourth week we're going to start talking about what design is, and then how to design stuff from there on out. Do you guys have any questions about how that all works? Okay. Real quick, assessments. So I'll do a quick assessment breakdown, right? So as I was trying to say before, there's your pre-exam marks, pre-exam, and then the actual exam. Okay. So the actual exams will have 60%. Your pre-exam stuff is 40%. And the way that's broken down is, I think it's like a weekly quiz kind of thing. But I think the first few weeks are grouped into the first quiz, and that's worth 10%. And that's basically all your material science stuff. And then you've got a few more quizzes. I think it's 5 of them, so it'd be 2 to 6. Since there's 5 of them, each of these are worth 60% each, and they're just weekly things that make sure that you're progressing well with the course content, right? And then in your exam, 20% of this 60% is the material science stuff, and then 80% of it is your design, your reinforced concrete design stuff. So basically this stuff is to do with reinforced concrete design. Reinforced concrete design. And this stuff is to do with material science of concrete. I say material science, but there's other topics, there's buildability and etc. But I consider it the more miscellaneous topics. Okay. Do you guys have any questions about how the assessments work or anything like that? No? Okay. Yeah, just keep an eye on the deadlines for each of these quizzes, because I can't remember which weeks the first one's due in. Maybe it's week 2, maybe it's week 3. But yeah, anyway, just keep an eye on the deadlines. All right, so in terms of concrete and cement, right? So concrete and cement are not the same thing. These are just screenshots of products that you can buy off the shelf at Bunnings, for example. A concrete mix will have cement in it. So if you think of an analogy concrete's like a cake, right? This is like a cake mix, is a concrete. Wait, no. Okay, anyway, so just let me cook with this analogy, right? So basically, concrete's like a cake, right? And cement is like the binder in that cake. So let's say, this is a bad analogy because I'm not a baker. I think the binder would be like egg or something like that, right? So cement is like the egg. And so you can buy the cement mix, which doesn't have all of the other bits, but a concrete mix has cement, so that part, And it also has fine aggregate and coarse aggregate. Another way of saying fine and coarse aggregate is like sand and gravel, right? So what's the purpose of sand and gravel? For gravel, which you've probably learned in soil mechanics, like large aggregates or like larger bits of rock, it's like a bulking agent, essentially. So that's just to make sure, like you can pour a concrete slab potentially with just cement, but it's gonna be really expensive. A cheaper material would be coarse aggregate or using aggregate, right? So you're bulking out this expensive material, making it more economic through adding gravel. And then the sand, which is the fine aggregate, is the main purpose of this. There's a few purposes, but the main purpose is to help with, so what I'm looking for, like kind of like sliding. So as you're like laying out your concrete, and if it only has gravel, it's not very, the word I'm looking for is workability. Right. If you add sand, it makes your mix a lot more workable, and it's a lot easier to push around on the ground as you're laying out the concrete. Yeah, so that's those things. Another thing to keep in mind is mortar. So I guess there's like two schools of thought, right? You can use sand and cement mortar, or you can just buy an off-the-shelf mortar mix, which has sand, cement, and lime. So you might be wondering, what does lime mean in this context? Lime is like another type of binder. It's a bit more old school than cement, but lime's a bit more flexible, less stiff than cement is. And yeah, so they're just two different types of binders that you use, modern cement and lime, which is a bit more of an old school one. And it just is better, this mortar mix is better for like placing between bricks, where it has to be a very specific shape and has to be like quite flexible. Okay, so yeah, that's just to give you context on what we're actually like talking about, right? So these are just off-the-shelf products. There are 7 standard cements in Australia, so that's split into your general purpose cements and then your special purpose cements. So I believe this one is a general purpose cement, for example, which you'll come to learn later is called ordinary Portland cement. Or OPC. So it's ordinary, so it's it's the normal one, and then Portland is a place in America where it originates from, and yeah. And then there's all these other types, but we don't really talk about the differences of like these mixes in this course. It's more about letting you guys know what is out there, and then one day if you're designing like stuff with concrete, you know that there's different types that you can use for various purposes, right? All right, any questions so far on cement? Cement bags, yeah.
You said that the bulking agent is so that we don't have to use as much cement. Is it stronger than cement itself, or is it like
strong, as in like, is a mix of
like if we just use
pure cement
as strong as we use concrete?
with the rocks and all that?
Yeah, like if we just use
I think it's actually stronger. I think we'll discuss this in week 3. I don't remember off the top of my head, sorry, yet. But we'll come back to it when we look at like the individual strength properties of cement, rocks, and then like the concrete mix as a whole. Yeah, I don't remember off the top of my head, sorry. Yeah. Do you guys have any other questions, or for now? No? Okay. So there's different concrete products as well. This is good to keep in mind. A lot of the time we work with normal strength concrete. So this is just to give you an understanding of like the relative values of everything. So you'll come to learn later that F-C is like your measure of strength. And specifically it's called the characteristic compressive strength. Again, this will be explained further in week 3. But we measure how strong the concrete is essentially based on its characteristic compressive strength. When we start to get higher than 50 MPa, we're in the territory of high strength concrete. So as you can imagine, this is used in like bridges and like larger applications and things like that. But the mixes are more expensive. They use different cementitious materials, which I think we'll discuss starting week 2 or week 3. But we use like fly ash and other different types of things that aren't OPC. So not things other than OPC will be introduced. And then, yeah, we've also got lightweight concrete, as you can imagine. It's just like not as dense. We've got 3D printed concrete. You've maybe seen a video of this. If you've gone on LinkedIn at all, you've probably seen like 3D printed concrete videos. Like, yeah, that's just like essentially the main purpose of this is that it doesn't need formwork. It doesn't need like this wooden shell around it to place it. Anyway. It's just a different methodology for placing concrete. And you've also got geopolymers, which now I wrote these notes a few weeks ago. Now I've forgotten exactly what this is, but it needs to be alkali activated, essentially. But yeah, anyway, we've got different concrete products out there. Okay, let's move on to cement production. Oh, does anyone need my notes, like a copy of my notes? Because sometimes I like go too quick and I scroll past what you need. So maybe I'll just leave this up for a second. If you're writing down anything that I like to scroll past, this is maybe convenient for you if you want to just have a copy of my notes as well as I'm talking. Yeah. Yeah. All right, cool. All right. Oh boy, yeah, there's lots to cover. Shit, I should go quicker. All right, cement production. So basically, you've got materials from the quarry that are harvested and then transported into like a cement production plant. It goes through a bunch of different processes, and I don't want to like spend too long on like talking about everything because it's covered in the lectures by Taewon, and Taewon's a lot more of like he's a lot more knowledgeable than me on especially the first half of this course. I'm not very good at the first half of this course, or first few weeks of this course. But Taewon's like an expert in cementatious materials, so he can cover all of these. And so if I skip over things, yeah, I won't have time to cover absolutely everything. The part I do want to highlight though is the kiln, right? So the rotary kiln, and essentially there's two versions of this kiln. You've got the wet and the dry version of this kiln, and the wet one involves adding water, and the dry one doesn't. That's basically it. And in terms of kiln length, the wet one's shorter and the dry one's longer. So rotary kiln is where you dry out. Sorry, it's where you produce clinker in the end. That's the whole idea. That's these little ball things, right? And then this is what ends up producing your cement, and that's a rotary kiln, which I don't know if it's AI generated or not, this image. Anyway. Okay, so what I want to talk about next is the oxides in cement notation. So most of you guys have either done chemistry or seen chemistry in some form, and then we've got a bunch of oxides here, like calcium oxide, silicon dioxide, and this is probably what you've come to expect. Oh, yeah, sorry.
I just want to say for the wet and dry kiln, the lengths are opposite. So
Oh, did I
that
spot?
one's roughly 200.
Oh, sorry. Okay, thank you. Whoops. I was doing this late at night. I probably got that wrong. Okay, thank you. Yes. All right. So, sorry, where was I? Essentially, what you have to get used to is this idea of cement notation. So because cement production and all these equations to do with cement are like, they use the same oxides over and over again. We don't need like a generalized form like we have in chemistry. We use very specific oxides, and therefore we can just shorthand them into single letters. So this is what we call cement notation, right? So it's just reducing like CaO into an expression just like C, or reducing SiO2 into an expression just like S, so etc. But yeah, anyway, this table is kind of self-explanatory. I guess maybe I'll highlight this column where it says like percentage weight of ordinary Portland cement. You can see the majority of ordinary Portland cement is composed of calcium oxide, and then silicon dioxide, and etc. You can read the rest. But yeah, so this is sorted by order of proportion, in OPC. Okay, next, cement minerals. So this is kind of like a new thing that you've probably not learned about, or you might have just learned about if you've watched Taewan's lecture. This idea that we have minerals that come out of the cement making process, right? Specifically, it's from the clinkering process, aka you bring your materials through the kiln, and then it produces these minerals, okay? You've got alite, bellite, aluminite, ferrite, and not gypsum. Gypsum is a mineral, but it's kind of like an additive mineral. I'll explain that a bit more as we talk about the next thing. But yes, anyway, OPC content-wise, this is the relative proportions. And what you can see is that here we were talking about different oxides, right? Like calcium oxide is represented with C, and etc. And silicon dioxide is represented by S. So now we take these oxides and then we're putting them in here, right? And so minerals are made up of these oxides, right? Like a combination of these oxides. So for example, alite has three calcium oxides to one silicon dioxide, right? And so its compound name is, like its formal scientific name is like tricalcium silicate, but everyone calls it alite, for example. And then there's dicalcium silicate, everyone calls that bellite. So just get used to these cement and mineral names, basically. Okay. Any questions so far about these ones? No? Okay. Cool. So anyway, back to the rotary kiln. We're going to talk about this a bit more in terms of you've got all the materials at the start and then the process through this kiln. This is the dry kiln. And yeah, basically I've just recreated what they have in the lecture slides, but in a slightly more nicely laid out way, in my opinion. Okay, so you've got the kiln and your input material starts here and then it makes its way down this rotary kiln to the end. And you've got different phases, right? The dehydration phase, calcination phase, solid state reaction phase, clinkering, and then rapid cooling, okay? And you can see the associated temperatures with these, both in my little bracketed thing and in terms of this temperature scale. So yeah, the temperature scale is on the right-hand side. It's quite a confusing graph, but just bear with me. You basically look at the red line, and the red line is associated with the scale on the right, okay? So you can see that it gets hotter and hotter, and then more hot, and then it plateaus, and then rapid cooling is where it cools down. Okay, the next thing we have to think about when looking at this little diagram is the mass distribution, right? So you've got all your input materials, and it's largely limestone, some quartz sand, some clay, some iron oxide, right? We're here. And because it's getting hotter, the water leaves the system, right? It evaporates out. Once it gets to this kind of temperature, 500 to 950 degrees Celsius, a chemical process known as calcination happens. It's where the carbon dioxide, you'll see the exact chemical equation below, but essentially one thing to note is just the calcium dioxide leaves at this stage, and a lot of the mass leaves as well. And then these new minerals form essentially, right? So in yellow, you can see free lime. So this is free lime here, this amount. You've got bellite is in this proportion. You've got some quartz sand stays, and you've got your calcium aluminates as well forming. So we'll talk about all of these things as well as we keep going. So yeah, that's a solid state reaction, and it forms all of these new cement minerals, right? It keeps getting hotter, and then here we actually see clinker forming, right? So before we just have free lime, we've got bellite, which forms quite early. What we really want is alite. So alite happens like later in this whole like clinkering process. It actually happens in the clinkering zone. But alite is going to make up the majority of the strength of your cement. And then another thing that happens is the calcium eliminates, gets so hot they become liquefied. All right. And then when the cooling stage happens, that liquid calcium, the liquefied calcium aluminates turn into these, sorry, one second. They turn into this and this, I believe. Did I get that right? Yes. They turn into aluminite and ferrite. So that's how everything forms, right? Okay, any questions so far? Screenshot. No? Okay. So yeah, there's a lot that's going on, but that's how you come to understand the whole clinkering process. All right, here's that chemical reaction I was talking about earlier. You've basically got your lime, and then carbon dioxide leaves the system, and you're left with calcium oxide. Yeah. So what I've got here for you, like what's shown on the screen, these are your molar masses of all of these. So if you remember your chemistry, these are all of the elements added up. So if you go like, you know, Ca plus C plus 2 of the oxygen, that's how I got that number, the 100 whatever. And this is not just a fun fact, this is like relevant for one of the workshop questions later. You'll see how you'll need to use like your understanding of like carbonation stoichiometry to work out some questions related to how much CO2 is released into the atmosphere. Okay? All right, any questions so far? Yes?
So what is the extra oxygen in it?
Oh. I think I copied this from the slides, but I think there's some weird thing going on where there's not, you know what I'm saying? Like there's not the right balance.
I think.
Or did I copy it wrong?
On the left-hand side, the oxygen is supposed to be 3 instead of 2.
Oh, okay.
That equation.
Sorry. Okay. So that's probably balanced now, right?
Yeah.
Okay. I might have just written that down wrong. Okay. Thank you. I'll fix these notes up as well after the class. I'm learning as much as you guys are about these things. Okay.
I watched your recordings last year.
Oh, thank you. Yeah. I don't even know what I said last year. I just blacked out and started talking to a camera. Okay. All right, let's move on, guys. All right, let's do some questions. So these questions are really, really simple, so they won't take very long. They're just bear with me. We'll do a couple questions, and then I'll give you guys a break, all right? All right, questions like, what is concrete? What is the component of concrete? Components of concrete. What is and then what is paste and what is mortar? Okay, so basically, concrete needs a binding agent of some sort. And let's just call it cement. And wait, one sec. I didn't fully write this down in my notes properly. Okay, basically, there's this. You need your fine ag, and you need your coarse ag. And then you need water to activate it. Okay, so that's what concrete is. What are the components of concrete? Water. Wait. What? I don't know what I was smoking when I wrote these notes, I'm not going to lie. All right, so basically, the components of concrete is what I wrote, right? So water, cement, fine ag, coarse ag. Okay, all right, let's do a better job answering that, right? Concrete is basically man-made rock. Let's call it that, okay? So, yeah, you're basically shaping whatever kind of rock-like material to your will, right? So, let's say we have a bit of formwork, right? So these are like the wooden bits. and you know, you get your struts and stuff like that. We've got a box to set up this concrete beam or whatever in, and you just pour it in, right? So you can shape concrete in many, many ways, okay? Concrete is essentially man-made rock. And yeah, all right, let's continue. So what is paste and what is mortar? Okay, so paste is just using cement together with water. You've got a paste, and this is like not structural, but you could use paste to like patch up stuff. Like say there's a crack on a wall, hopefully it's not a structural crack, and you just want to cover it up, you can use paste to just cover that up. Mortar is cement, oh, what did I say? Water, sorry. And you need fine ag, like sand, okay? Now we talked about this just has to be some kind of binding agent. It could be cement or a combination of cement and lime, but yeah, essentially mortar is what you use to make a brick wall, basically, right? Okay. Any questions about that first question? Okay. Question 2. In modern cement production, ground and mixed raw materials enter a preheated tower before going into burning kiln. This process is also called dry process kiln. Discuss the advantages of using a preheating tower. So the preheating tower makes it so that your material is already hot before it goes into the kiln. So it reduces the length that you need your kiln to be. That's one. And second one is that the preheating tower has a way to recycle the hot air. So it increases the energy efficiency of your system as well. So that's 1 and 2. Okay, question 3. What are the main oxide components, what are the main oxide compositions of raw materials to produce OPC? And write down the chemical formulation with the cement notation. Finally, write 4 cement materials using the mineral names. Yeah, you can read all that. Okay. So the first one is calcium oxide. And calcium oxide has the cement notation of C. Next, we've got silicon dioxide. And that's got the cement notation of S. Next we've got aluminium oxide, or sometimes called alumina. That's Al2O3. And that's abbreviated with A. And then we've got iron oxide. That's abbreviated with F. Okay? So yeah, those are the main oxide. Those are the main oxides that go into OPC, right? Now, I'll get back to gypsum. I'll talk about that later. Okay. All right. Oh, sorry, I wrote that in the wrong spot. That's so CaO is C, SiO2 is S, yeah, A, F, and then water we do as H. Okay, and then lastly we've got the cement minerals, right? I'm going to write it in blue to make it clear that I'm writing in cement notation, right? And that's, as you see there, that's alite, belite, aluminate, and ferrite written in cement notation, as well as its associated chemical notation, right? I can see people still writing, so I'm going to try to do this half zoomed out. Right. Question 4. List the main thermal zone in a list the main thermal zones in a cement kiln, and then describe the process in each zone. All right. So zone 1, we've got the dehydration zone. So that's where you've got the water escaping because it's getting hotter and hotter, and then the water evaporates. That's the free water, as well as the clay will have pore water, right? So that also gets evaporated out, okay? Stage 2 is calcination. All right, and then calcination has this reaction. Oh yeah, you're right, by the way. That is a 3. Yeah, good one, good catch. Yep, so that's the calcination reaction, the proper one. All right, number 3 is the solid state reactions. The solid state reaction zone. And that's basically where you have your belite forming. Belite forms quite early on. And then number 4, you've got the clinkering zone. And that's where your alite forms, and that's what we're looking for. As much alite as possible in order to maximize our cement strength. As well as you've got the calcium illuminates liquefying. All right, then you've got the rapid cooling zone as well. So that's where the system's overall temperature drops, and the calcium illuminates, which are in liquid form, resolidify, and then they become your illuminate and, I forgot the name, ferrite. As well as some of the, alite solidification depends on fast cooling. Well, I think that's self-explanatory, that sentence. All right, I think we've got one more question before we go on the break. But yeah, this question, oh, sorry. You guys copying that? Shit. I don't know how fast to go. You know what, I'll just show you the QR code again. I'm gonna scroll past, so if you need the notes to copy down, just scan it out. Okay. All right, question 5. There are 4 zones in a burning kiln before cooling. Which zone is involved in the biggest mass loss, and what is the main cause of this reduction in mass? Okay. So basically, it's the calcination zone, right? This is easiest to see visually. So if we go back to the clinkering diagram, you can see how this was the starting mass, and it drops all the way down to here. Okay. So that drops significantly. And that's all of your CO2 leaving your system due to decarbonation. And then B, in raw materials, in raw materials, what the hell is this? Raw materials composed of 65% of limestone, 18% of quartz, 12% of soil, and 5% of Fe2O3. Let's assume that there's no moisture in the raw mixture and all the particles are fine enough to be exposed at the uniformly high temperature. Please estimate the weight fraction of the gas emitted. Also, with respect to the production of this gas, discuss at least one method to improve the global sustainability in construction of materials. Okay, so here's where we need to use our stoichiometry. Okay, so we've got, this is the wrong bloody formula again, isn't it? You've got these molar masses added up. And basically what it's saying is we want to calculate the amount of CO2 released. We're saying basically because we're looking at the limestone, right? What we care about is the fact, like this first line, right? We care about that our raw materials have 65% of our raw materials are the limestone. Okay, so first we do 65%, right? And then we're going to multiply it by this number, which is the molar mass of just the CO2. So there's the molar mass of the carbon dioxide. And then we divide that by the molar mass of the limestone. Okay, so we go like this, 44.009 over 100.086. So just to highlight that again. Okay, hope no one's colorblind. All right, so we basically multiply all these things together, and then we get 28.581%. And that's our answer. So 28.581% 0.581% of the raw materials have left the system and escaped to CO2. Does that make sense? Yeah? Okay, cool. And then we'll quickly discuss this other part. Discuss one method to improve the global sustainability in construction materials. So this is kind of like looking ahead, but OPC, the ordinary Portland cement, is a fundamental part of making cement. You can't avoid using it, but it's the part that it's the material that releases the most, in using this cement, you're going to have to undergo decarbonation, and you've got CO2 being released in the atmosphere like during the production. But what you can do in your cement and concrete mixes is find partial substitutions. So we'll be talking about this when we talk about like cement admixtures, right? But you don't have to use 100% OPC. You can use fly ash, you can use silica fume, and etc. Those are alternatives that don't produce CO2 into the atmosphere. Does that make sense? So that's one way that you can be more sustainable. You can use different concrete mixes that don't just use OPC. And in fact, the general purpose cement isn't actually 100% OPC. I should probably mention that. The majority of it is OPC, but in our general purpose mix that you can buy off the shelf, it's already got partial bits of fly ash and silica fume, etc. Well, I think fly ash, but anyway. We'll talk about that in a few weeks again. Yep. All right, guys. So that brings me to halfway through my workshop. I'll give you guys a break. You got 5 minutes. You can talk, stretch your legs, go to the bathroom, whatever. We'll start again at 2. Hello.
Looking at like just the signal force itself, right?
Mm-hmm.
Wait, so do you need to do 192 units of credit? Is that what it is? 160?
192 from off the top of my head. Yeah.
So does that mean I have to do like 4 disciplinary electives and like 4 gen eds? Because it was like 2 gen
I think it's
eds.
two gen eds, yeah.
And then 4 basically. What's a 3 elective? Is that just like can be?
I think that's a gen ed, right? Or does it say gen ed?
Yeah, it says gen ed here. It says disciplinary elective, and there's like 3 electives. I don't know what the 3 elective is.
That's interesting. I'm not too sure. Actually, this has changed since I took it. Yeah, because there used to be 5 discipline electives, now there's 4. So they could have moved something around, I'm not sure.
Also, do you know what happened with... Okay, this is like come back at my whole cohort, right? Do you know what happened with Steele's marking last try?
I've got a microphone here.
Oh.
It's probably not good. I'll talk to you later about it. Yeah.
take a while. Is that why you can like start it?
I don't know why it's so hard to see the front. I tried to dim the lights, but I don't know if that is that better or worse. I think it's because all the light from over there. I can't do much about it. I think.
Yeah, I saw it. No, it was not. It was like that. Yeah. Yeah, it's the same thing, bro.
All right. Let's keep going. Okay, so before we move on to the other questions that I've got prepared, let's talk about hydration. So basically, what you can see there is paste, right? So that's cement mixed with water in a little like lab dish or something like that. Can't quite see. So yeah, this is basically the second lecture of the first week, content related to that, right? So basically, there's a few definitions that I want you to familiarize yourself with. One is your water to cement ratio, right? And that's by mass. So yeah, basically, we're talking about the mass of water divided by the mass of the cement. And then we've got the mass of cement. Sorry. Basically, this is like already a rearranged equation of it, right? But you can find the mass of cement using this fraction, right? So you get the mass of your paste, so this mixture, like the mass of whatever this is, and then you divide it by 1 plus whatever your water to cement ratio was, right? And that'll give you what the mass of the original cement was. You've got evaporable water, and you've got non-evaporable water, which I believe I've got a picture of it. Yeah, I'll show you here. So evaporable water and non-evaporable water, let's talk about that. So here's a heated sample, right? You've got your paste, right? And then that weighs some amount. And then if you heat it to 105 degrees, so that brings it past the boiling point of water, you've got an oven-dried mass. So all the free water is now left the system. But then if you further heat it to 1050 degrees, we've got your mass after ignition. So that temperature is like an ignition temperature. It's like so hot that some stuff happens, basically. Right? Okay. So in terms of your evaporable water, right? That's what can be boiled out, right? And then your non-evaporable water is the extra water that leaves after you've ignited it, right? Or gotten so hot. And yeah, you'll realize that because what we're looking for is this quantity called degree of hydration, right? It's useful to express your non-evaporable water, aka the water left between this stage and this stage. It's useful to express this in terms of how many grams of water to the amount of grams of cement that you had to begin with, right? and that gives you your degree of hydration. And the reason that's useful is because there's a very predictable amount of non-evaporable water if you have fully hydrated paste, right? So you've probably seen the lecture slides. Well, I don't know if you've seen the lecture slides, but if you have, you know that like an optimal amount of, sorry, wait, let me think about what I'm saying. The optimal amount of water to add to paste is like 0.23 as a ratio, right? And so to fully hydrate your paste, you need to have like that at the 23% mark, right? And because of that, our degree of hydration is just the ratio of how much your paste was hydrated. That makes sense. So you have this like, yeah, you're measuring it based on this relative scale, okay? That didn't make any sense, but okay, you'll see what I mean when we do the question. All right, so now we're going to talk about rate of hydration. So hydration reactions, I read that wrong. We've got, this is what happens when you add water to alite. This reaction happens, and this, keep in mind, this is in cement notation. And then this is belite, and then you add water, and then this is what happens. And we call the products, the stuff on the right-hand side, the hydration products. And yeah, this is what happens when you have aluminite. Is that supposed to say illuminate? Yeah, as well, and what happens when you hydrate it. Okay, so hydration products, right? These are the things that end up in concrete, right? So before we were talking about the kiln, right? And we were talking about what cement minerals end up in your cement powder, right? And that's like a dry product. And then when you mix it with water, the whole thing's hydrated, and you get, and because there's different chemical reactions now, there's this hydration process, you get hydration products, right? And then these set, and you've got concrete. Okay, so what are these? You've got portlandite, right, which is just a nickname for calcium hydroxide. You've got calcium silicate hydrate, and then you've got attringite and monosulfur aluminate, right? And those stem from the parts which aren't alite and belite. So basically, alite and belite, when they're mixed with water, will form these ones, right? Portlandite and your calcium silicate hydrate. But your aluminate will form these ones, right? Attringite and monosulfur aluminate. So one question you might have is basically like, what's the difference between these two, right? These hydration products. And because they kind of happen simultaneously. And I believe it's depending on if there's an excess of gypsum or if we don't have enough gypsum to feed into the system. So gypsum's like an additive. Actually, I might be able to show you it in the, sorry. Yeah, so gypsum's added like later basically into your final cement, your dry cement product. And it serves kind of two purposes. The first purpose is that it helps your illuminates, one sec. It helps your illuminate form attringite. And the second thing is that, do I have the graph on this week's notes? Oh, I do. Oh, well. I've still got a while to talk about. Okay. Basically, the gypsum helps the, one sec. I've got this. Basically, we want all of these reactions to happen when we hydrate our cement. We want all of these different reactions to set at the same time, right? So imagine you've got like a concrete truck, right? You've got a concrete truck, and it's got the cement inside, and you've added water and stuff like that. The idea is that we have 2 hours thereabouts to place this concrete before it sets, right? You want all of these individual reactions to go off and set at the same time, right? But they actually have different reaction speeds, right? So the purpose of gypsum is to slow down the ones that go too fast, right? So they all land at the same time. Okay, I think I cooked there. All right, all right. Okay, whew, recovered that. Okay, so that's basically these hydration reactions. And yeah, basically if I just keep scrolling down, you'll see how this comes together, okay? So you've got different stages of reaction, and on this graph in particular, you've got your heat evolution, right? So this heat evolution versus time, so this is how hot it gets, right? So it starts off very hot. You've got kind of like this initial reaction once you've added water into your, say like concrete truck. And then there's not much reactions happening, right? And it's relatively cool, right? And this is your placement time, essentially. So stage 2 is your dormant period, which you want to transport your concrete on your truck, and then you want to place it wherever you want it to be. And then once it's placed, so ideally you've placed it before this part starts happening, you get a new start of like a heat evolution, right? So your concrete will get very hot again once all these reactions like fully go off, and now your concrete wants to basically solidify and cure. Okay, so acceleration stage, this is your initial set, right? So this is the acceleration stage, and that's where everything's like setting. And then basically your heat will lower, and there's this is called the deceleration stage, and your concrete's not workable anymore. It can't really be moved and manipulated. It's going to set in place, right? And then from stage 5 onwards, it's relatively stable in terms of its chemical reactions. It's still going to have like small reactions that happen over time, but it's relatively steady, which is why we say that's a steady state. Okay, does that make sense? Okay, fantastic. So hydration products over time, right? So over on the left here, we've started with all the materials that we'd expect from your dry mix of cement. And then, you've added the water, and after you added the water, like off it goes, and it forms these products in the end, okay? So, oops. Yeah, basically these products are formed, right? And there's some amount of chemical shrinkage, which we'll talk about either next week or week 3. But yeah, so you go from porosity, pore solution. Yeah, you go from, let's see. Is there anything to talk about, really? Okay, sorry. This is confusing. I think this is the one that's presented in the lecture slides. Sorry, just go over this. So the idea is that it gets less porous after it's been reacted with water. So voids will form, right? And then this is the idea of shrinkage, which, again, we'll explore more next week, okay? All right. This is why you should watch Taewan's lectures on this topic. Okay. And we've got properties, and we'll talk about the strength of all these as well. Yeah. Basically, this was your alite. This is your bellite. This is your, it was aluminite, right? And ferrite. And that's gypsum. You've got the reaction rates, and then they make these hydration products, right? And then this is the amount of heat that they produce, and then this is the strengths, right? So I want you to pay attention to these two, right? So with your alite, right, the reason why we wanted a lot of the alite in, like from the clinkering process is because when it's hydrated, it's going to basically give you the most strength, right? And so this is going to result in the highest amount of concrete strength. The bellite basically gives you a low amount of initial strength, but then over time, it's going to get stronger. So that will give you like a lot of your late stage kind of concrete strength. And that's kind of why if you compare like concrete's 1 day strength to its 28-day strength, right? So 28 days after it's set, it's going to be stronger than its 1 day strength. It's because the bellite and the associated hydration products are going to react and give you your final concrete strength. Okay, all right. So this question just says, sketch the schematic heat evolution curve of cement hydration indicating the various stages involved in the cement hydration. Now, it's basically recreate the thing you saw in the lecture. That's what the question is. But yeah, I'll just briefly cover it. So stage 1 was the heat evolution stage. That's there. Stage 2, the dormant period, which is here. Stage 3 is the acceleration stage. So at this stage, at the start of stage 3, you should have placed your concrete on site. And then you've got the acceleration beginning. And then stage 4, you've got your deceleration. Your concrete is getting less hot and it's not workable anymore. And then stage 5, you've got your steady state. Yeah, there's a lot more details there that you can see, but that's the premise of it. Okay, question 7. Oh yeah. All right, so now we're going to do a quantitative example. So I'll go through this one slowly. So just recall the stuff that I was talking about here with your definitions for your paste samples and things like that. And just keep in mind the definitions of evaporated water and non-evaporable water based on how hot your sample gets in the lab. Okay, so in a lab, paste was prepared using 45 grams of water and 100 grams of cement. All right, so immediately that tells you your water to cement ratio was 0.45, right? Because you've got 100 grams of cement, and for every 100 grams of cement, there's 45 grams of water. Okay, so that's your water to cement ratio. It's then sealed to prevent the loss of water and was cured for 3 days and 7 days in a constant room temperature. After the specific cooling period, the paste samples were taken and then dried in an oven for 24 hours. So that's your, sorry, one second. That's your oven dried, like basically it's about to tell you the oven dried mass. And then the samples are moved to a muffle furnace and burned for 2 hours at 10,050 degrees Celsius, right? So that corresponds to oven drying. That corresponds to ignition, okay? The masses of each sample were summarized in the following table. Please find out the amount of evaporable water and non-evaporable water, and also calculate the degree of hydration of the paste. Okay, so the idea is that you've got 2 different samples. So for this question, we're going to be doing the calcs twice, right? One for sample 1, once for sample 2. And essentially, that's your evaporable water, the difference between those 2 things, and that's your non-evaporable water, okay, the difference between those 2 things, all right? All right, so the first step is to find out how much cement was in the samples. And the way that you do that is you input your water to cement ratio into this formula, and it gives you, find mass of cement in samples. Yes, okay, sorry, okay. Basically, let me scroll up. the mass of cement we know has this like formula, right? The mass of the paste over 1 plus W over C. So we've swapped that around. Okay, anyway, sorry. Sorry, I made these notes a long time ago. I have kind of forgotten what's going on. Let me think about this for 1 second. I'm just going to paste this here and look at it for a second. So this has been moved to here. Okay, I understand what's going on. All right, okay. So this is your mass of the paste, okay? So this is the mass of the paste. That's the mass of the paste. All right, so that's for sample 1. That's for sample 2. All right, that makes sense now. So now this is 13.224. And so these are the values that we have from the table, and we've just put it into this formula, okay? What we're interested in is solving for the mass of cement, right? So when we rearrange this equation, right, we're rearranging for this, and we know all the other things. So we basically just divide both sides by 1.45, right? And we get the mass of the cement is 7.56 grams and 9.12 grams, right? So that's for sample 1 and 2. Okay. All right. Okay. So that's step 1. Step 2 is we want to find the amount of evaporable and non-evaporable water. So that's just a matter of comparing this number with this number and this number with this number. So that's for your evaporable water, okay? So we go, sorry, there's just like a lot to look at. I might do highlights. So that, and that, that, and that. I don't know if this is more or less useful. There we go. All right, so we're just putting these numbers in, and we take the difference, and we get 2.62 grams and 2.93 grams. Yeah? All right, in terms of non-evaporable water, it's similar, but let's do different colors. Do red highlight and different color, orange. Okay. Let's do red. Like that, okay? So we're taking the difference as well, and we go 0.783 grams, and we go 1.173 grams, okay? So that's for sample 1 and 2. All right, step 3, we're gonna, like in the end, we want the degree of hydration, right? So that's represented with alpha. So what we do is we get your non-evaporable water and divide it by the mass of the cement, and that will give us your non-evaporable water as a ratio of how much cement you have, okay? Which will be useful for the degree of hydration formula, which you'll see. Okay, so basically the non-evaporable water, which we calculated a second ago, I ran out of colors to highlight with, so I might just do boxes. So blue box, red box, okay? So blue box is here. Oh, I'll just do it in color. So that's 0.783. This is 1.173, okay? And we divide that by the amount of cement that we have. Oops, sorry, 1 sec, let me just write this down. So that is a highlighted one. We go red, oops, orange, okay? So we get these numbers, right? Okay, and then that gives us these ratios, basically. So that's our non-evaporable water in terms of grams per 1 gram of cement, okay? All right, now I'm going to do different color boxes. all right? So purple box and orange box, okay? So what we want is the purple box, 0.104, and orange box, or orange, 0.129, like that. And this is a set number, okay? This is always 0.23. That's what I'm trying to say, is the optimal amount of hydration in your cement, okay? So hopefully that ties together what I was trying to say earlier and explaining poorly, all right? Yeah, so that's how we do it. And once you compute this, gives you the answers that you're looking for. So these are the degrees of hydration, okay? That's the answer. All right, we've got 2 more questions, but they are fairly straightforward. Do you guys have any questions on how to calculate this? Because this is like a quantitative question, and you can possibly expect to see this style of question in your finals, okay, for the material science part of your finals. I can see people copying this down still. I'll just give you a second to do it. A lot of people writing. I'll come back to it, all right, if you guys are still writing it. All right, so question 8. So this brings us to our last 2 questions, all right? Question 8 says, there are 4 cement minerals. What is the order of the rate of hydration during the first few days? So the fastest one is illuminate. The second one is your alite, right? That's the next fastest. The third one is your ferrite. And the slowest one is your bellite, right? So bellite has the slowest rate of hydration, right? So when we do our whole adding gypsum and the quantity of gypsum that's added to cement mix, the way that they figured out how much gypsum to add is how much do you need to add to your mix such that these faster reactions coincide with the slowest reaction, right? So gypsum's like slows down the faster reactions, I guess, right? Does that make sense? Yep, okay. So those are the speeds of hydration. All right, question 9. Explain the role of C3A, C3S, C2S in the rate of hydration and write the hydration products of them. Also explain the role of gypsum in the reaction of C3A. Sorry, yeah. So C3A, right? C3A is your illuminate. Did I spell that right? Yeah. And basically, it has a really fast reaction, but gypsum is used to prevent the reaction from starting immediately, and also releases a lot of heat initially. It forms a tringite. All right, and then we've also got, this one is alite. And alite, if you've made your clinker properly, is more than 50% of Portlandite cement. It reacts quite fast, the second fastest, and then it also releases a large amount of the heat. And these products correspond to the majority of the strength of your final concrete, right, once it's set. Next we've got bellite. Bellite is similar to alite, but the rate of reaction is very slow. It releases much less heat. And it contributes to the later strength development. And since it has like really slow reaction, it'll react over a long period of time. This is why, let me just draw a graph, maybe explain what I'm trying to say better. Let's just say this is your characteristic compressive strength, and then this is time. All right, it might look like that or something. So let's just say that's 1 day. After 1 day, that's how much strength you would have. And then this isn't really drawn to scale, but let's just say at 28 days, it's mostly plateaued, your strength, right? this is largely due to the bellite. Sorry. Yes, this is largely due to the bellite in the clinker. Okay. All right, that brings me to the end of the workshop. I know some of you guys were copying down. Were you copying down this question or the previous one, or I don't know. All right, let me know if you want me to scroll down anywhere. You copy down. All right. Anyway, that's the end of my workshop. So I'll see you guys next week.